Okay, so how about if we take something like 32, let's go. So we're gonna find everything. In other words, we're gonna, well, let me say that. Okay, so we're gonna make a table, get everything in the table, and then our goal at the end is to have the table so complete that we could easily draw a sketch from that. So what do we do with this? We're gonna use all our calculus stuff. That's probably the first thing we always wanna look at. What is it again? Okay, domain, right. Are there any excluded values here?
Square root of 2 squared.
Okay, so look, the bottom could be 0, right? When would the bottom be 0? X squared minus 2 would equal 0 when x squared equals 2. So we get plus or minus the square root of 2, right? So we know that x cannot equal plus or minus the square root of 2. I'm not going to write it in interval notation. I'll just write it that way, right? Okay, so what about derivatives? Say it again. Oh, and let's do it. We can do end behavior too. Sure, let's do that while we're there on that first. You know, there's no set order to this, but we've been talking about end behavior. Let's do that. So what's going to be the limit of our function x squared plus 1 over x squared minus 2 as x approaches plus or minus infinity? What are we going to get? 1. Yeah. Okay, so our end behavior is 1, right? So we'll add that to the table. Okay, let's take our derivatives here. How am I going to do the first derivative? Got to use quotient rule, don't I? So low d high, what's d high going to look like? Good. Okay, keep going. Low d high minus high d low. What's d low? Good. All divided by. Okay, so we can clean that up a little bit. Let's see, we could factor out of the top. Looks like we could factor out of 2x, right? Leaving us with x squared minus 2 minus x squared plus 1. So what's that become? Negative 3, I think. Everybody see that? Here, I'll show those steps. So we get from this, if we factor out the 2x, we're just going to get an x squared minus 2 minus the quantity x squared plus 1 all over x squared minus 2 squared, which is just equal to, those are going to cancel. If I distribute the negative, I just get negative 3 times 2x, so that's negative 6x over the quantity x squared minus 2 squared, right?
But you cancel out.
Say it again?
You cancel out the 2x? Oh,
No, the 2x got factored out front, yeah. On the bottom, no, I can't cancel anything there because the x squared is buried inside something that's being squared, right? What's the,
Like if you separated into x squared minus 2 times x squared, would you not cancel out the whole top x equals 2?
you mean this one right here?
Yeah.
Well, I can't because this isn't a common factor. It's just a term, right? It's not, 2x is a common factor because when I factor it out, how many factors do I have here? I've got 2x times whatever's left over, so I've got 2 factors. You can only cancel common factors vertically. You can't cancel a term. That'd be like saying this, like if I had x plus 2 over x, I can't cancel those, right? See what I'm saying? But I could if I had x times the quantity x minus 2, so now that's being multiplied, so it's a factor, then I could cancel it, right? Okay, so there's our first derivative. Now, if we're not trying to find an inflection point, do we probably want to take a second derivative here? No, we don't want to deal with the quotient rule. But because we're trying to find inflection points, we're going to take it, okay? Before we do that, what are the critical numbers of the first derivative? All the places, well, you fill in the blanks. When the bottom equals 0, where would that be? Plus or minus radical 2, but is that in our domain?
No.
It's not, right? Those have already been excluded. So those are not critical numbers, right? Critical numbers have to be in the domain, right? So we don't have to worry about the bottom. And you're going to see this pattern. If there are some values that make the denominator equal to 0, guaranteed, the math gods work all this out. So when you take derivatives, those exclusions will just get propagated from, the parent is the original function, and then the first derivative is a child of the, right, and the second derivative is a child of the first derivative, and that's the relationship we call it. And so they're always going to inherit all of those exclusions, right? But that's not a critical number because it doesn't even exist, right? What's going on there at plus or minus radical 2? What is it?
A whole, right?
Okay, which one is it now? Is it going to be what are the two possibilities? If the bottom is 0, what are the only two things that could be happening? Could be a vertical asymptote, or it could be, well, it could be a hole too, right? It has to be excluded from the function. Could be a vertical asymptote, or it could be a hole. But in this case, very clearly, which one is it? It's an asymptote. How come? What's the difference between a hole and an asymptote? A hole is when you have a 0 of what? Got to make this connection. You will. I mean, we'll do this a ton. Think back to our limit stuff. When did we have a hole and when did we have a vertical asymptote? Vertical asymptote is when you have a unique 0 of the denominator, right? So it's a 0 of the denominator only. A hole is when you have a shared 0, top and bottom, that we have to cancel somehow, right? So in this case, plus or minus radical 2 is a 0 of the bottom only, right? So what is this? Vertical asymptote, right? And so that's why in a vertical asymptote, obviously you can't have critical numbers there because the function's not defined there. So what's the only critical number of the first derivative?
0.
Yeah, y prime equals 0 at x equals 0, okay? Second derivative. Quotient rule again. So we get, what do we get?
2 times x squared minus 2.
So we get, well, what's our little saying?
Low.
Okay, low d high minus high d low, right? So we get our x squared minus 2 squared times, what's the derivative of the top?
Negative.
Okay, good. minus the top times the derivative of the bottom. What's the derivative of the bottom?
2 times x squared.
There we go, chain rule, right? So we got derivative of hand squared is 2 times hand to the 1. And then there's another there,
Times 2x.
all divided by the bottom squared, which becomes what? Yeah, the fourth power. Okay, good. So we get x squared minus 2 to the fourth. Okay? All right, so we got to clean this up. So on the top, what could we factor out?
X squared minus 2 is
Good, we could take an x squared minus 2 to the first power, right? And then we could take out, it looks like maybe a 2 also.
negative 6. You can take out a 2.
Well, we could take out a negative 6 too, couldn't we? Right. We can't take out an x though, because we don't have an x in this term. But we could take out, they share that negative 6 we could take out, and then we could take out an x squared minus 2, right? So we could rewrite this then. So if we take out a negative 6 times the quantity x squared minus 2, what's going to be left over? Okay, from the first term,
X squared minus 2.
yeah, all we're left with is x squared minus 2, right? We've divided away this, one of the two that are being multiplied together, and we've taken away the negative 6, right? Okay, what's left over here then? So we're taking away, on this side, we're taking away the negative 6. We're left with an x, and we've divided that away, right? So we got negative 4 x squared, right? Everybody agree? Did I get that right?
There's 2x.
Because I've got an x there times an x there gives me an x squared. I've got a negative, that negative is gone. So I've got negative 2 times 2, negative 4. Everybody agree? Okay. And then that's all over x squared minus 2 to the fourth, so
Could you
I could, right, because I've got a common factor there and there, don't I, right? So now we could cancel one of those, leaving me with power of 3 on the bottom. Then we could combine stuff in here. And what's our simplified form of that then? We get negative 6 times, what are we left with? X squared minus 4x squared is minus 3x squared. And then negative 2 minus 4 is minus 6.
minus
Did I do that right?
negative 2 times? It's just gonna be 2.
We don't really need this. We don't need those first parentheses, do we?
No, it should have been plus
Did I screw something up here?
x squared. The negative 6 should be negative 2 in your parentheses. There's no negatives.
Yeah, what are the negatives?
Because the negative 2 isn't one.
Oh, you're right. Yeah, you're right. Yeah, you're right. Negative 2. I got you. Yep. I don't know what was I doing there? I don't know what I was doing. Minus 2. There we go. Oh. Okay. It's a 2. Make sure you see that. Okay, so then we could, well, one thing we could do that's really just simple, I won't even make another line. Why don't we go ahead and just distribute the negative and make that a positive, right? Okay? So there's our second derivative. So do we have any critical numbers of the second derivative?
X.
Mm-mm. None, right? because the bottom is 0 at the vertical asymptote, and the top is non-zero, right? So top is positive valued always. Agreed? Okay, because x squared is non-negative. Okay, so then we get no second derivative critical numbers. We got a first derivative critical number at 0. Let's just summarize all this stuff. So we get, yeah, let's just summarize this. Let's go to a new page and summarize. It's too messy. We want to make our table. We just want to have only the things we need. So okay, so that's important. This was important, right? That's important. We got a simplified first derivative right here. And simplified second derivative right there, right? Okay, so let's make our table. So our domain was all reals except plus or minus radical 2, right? So at negative square root of 2, that was undefined, our function was undefined, and at positive square root of 2, our function was undefined. So what do those become? What's going on there? You guys told me.
Asymptote.
Asymptotes, okay, so then we can do this, right? We can say vertical asymptote, and those are going to break up our function. Okay? We had a first derivative critical number at 0, right? So at 0, we have a 0 there, which is a horizontal tangent. So what can we do with that? Well, you don't even probably have to do that, right? If the first derivative is 0 at 0, let's use the second derivative test, because we went through the hassle of taking the second derivative. So what's the sign of the second derivative at 0? If I plug 0 in, I'm going to get positive on the top and negative on the bottom, right? And so it's negative, isn't it, right? So if it's negative, what's that tell us? 0 first derivative plus combined with negative second derivative. It's got to be a maximum, doesn't it? It's got to be concave down and a horizontal tangent, so it's a max. Okay, so there were no critical numbers of the second derivative, right? And no other critical numbers of the first derivative. So what can we say something automatically about the values of the second derivative to the left and right of that asymptote? Like if I were to pick test points, let's say at 10 and negative 10. Can I just assume it's negative in those places? It's a kind of an interesting question, isn't it? Because what's the only way that a second derivative can change, that we've talked about, that a second derivative can change concavity is at an inflection point, right? But remember, say it again. Right, have to be critical numbers, and there were none, right? So you might think, well, it can't change. But asymptotes are like different universes, right? They're like black holes. And so when you throw in vertical asymptotes, things can completely change when you cross the asymptote, right? Different universe. So we know that in this universe over here, to the right of the asymptote, there are no second derivative critical numbers. And so it can't change concavity in that universe. It can't change concavity between negative radical 2 and positive radical 2, right? But we still need to check a point over here. So at 10, what's the sign of the second derivative? I'm going to get positive over positive, right? So we know it's going to be concave up everywhere in that universe, right? What about at negative 10? Positive everywhere, right? Okay. Okay, good. So that's a lot of stuff we got in there, isn't it? Right? What about our limits? We can do those too, right? We can just say the limit as x approaches negative infinity is what? 1. So that's telling us right there, horizontal asymptote, right? The limit as x approaches positive infinity is 1. So we interpret this whole part right here. We just focus on that part of the table. That's telling us horizontal asymptote is y equals 1, right? So even that stuff gets put in the table. Okay? We could put zeros in the table, right? We already know about that. If I evaluate the function at 0, what do I get? Negative 1/2. So there's a point to anchor our sketch. Okay. All right. Are there any x-intercepts anywhere? Any place where the function equals 0? My original function. Fraction equals 0 where the top equals 0. The top ever equals 0?
No.
No. So there's no x-intercepts. So that's probably all we need to make a sketch of this thing, isn't it? Right? If we want to anchor a point out here, we could. I mean, like, we could pick a point at, what would be a convenient one? We could pick a point at, like, 2 or something if we wanted to. If I plug in 2, let's just see what we get. If I plug in 2, I get, what, 5 over 2, so 5/2. I could make another point if I want to get more specific. One more thing. What about, is there symmetry? Look at the original function. Does it pass any of the symmetry tests? Right? Have we reviewed symmetry? We talked about it not a little bit, maybe not a ton. Okay, well, we'll come back to that. Let's make a sketch first, and then we'll go back and look at the symmetry. Okay, so how are we going to sketch this then? So here's our x-axis. There's x equals 0. So that's our y-axis. At 0, 1, negative 1/2. So right there, we have a maximum. We have vertical asymptotes out here at square root of 2, so that's about there. Ish, right? So we know we get vertical asymptotes there. Right? So what's the sketch look like in between? We know. There's only one thing it can do. If that's a maximum, we got these vertical asymptotes. Yeah, we know it's doing this, right? Okay, done. Perfect sketch. We know exactly what it looks like. How about here on the ends? If there's no x-intercepts, we know we got one point that's positive here, right? And it's always concave up, and we forgot one asymptote. We get a horizontal asymptote at y equals 1. Now you really get a taste of how useful these asymptotes are, right? What's the only way that I could have, if I could have a function with no extrema, right, it's boring, that's going to adhere to these two asymptotes, that's always concave up. There's only one thing it can do. Yeah, it's got to do, exactly, it's got to do this, doesn't it? Right? Has to. Over here, same thing, right? If it's concave up, no extrema, it's got to do that. Right? So it does have symmetry, doesn't it? Right? Isn't that pretty cool? I mean, all that stuff, that table gives us that whole function. And that's pretty accurate. I mean, if we were to graph that thing, it looks just like that. Right? So symmetry. I want to just do a brief review of this, if you guys aren't super familiar with it. Okay, we could have added one more element, which is symmetry. Now we know what our test, how much time we got? 5 minutes? Okay, we're good. So our test for even symmetry, if I input f of negative x, what do I get back if it's even?
Oh, the same.
Same thing, I just get back f of x. That's even. What's our test for odd symmetry?
If you can take out a negative 1.
Okay, good, so that, right, okay. What do the names even and odd mean?
Where it's reflected over
But we call this even symmetry and odd symmetry. There's a really important reason for that. It's because it has to do with polynomials. Even means that it's a polynomial with only even powers of x. Odd means it's a polynomial with only odd powers of x, right? So let's look at this, at the polynomial on top. That's the same as x squared plus 1 times x to the what? 0, right. Those are 0 and 2 are even, right? So the top is even, agreed? What about the bottom? I got an x squared and an x to the 0, so that's also even, right? So now what do you think happens here? This is where so if we take a rational function, and they don't even have to be polynomials, they could be trig functions or anything. If I have even divided by even, what do you suppose the outcome is? Even, yeah. What if I had odd divided by odd? Even. Even divided by odd or vice versa is odd. Yeah. Have you guys talked about that? Just okay, it just makes sense to you, but that's true. That's true, yeah. And so because you right, and that's the other useful, the advantage of labeling it even and odd is you can make an analogy, and math gods are wise this way. You can make an analogy just to numbers, right? Too. Okay, so yeah, so we can say from the beginning then, because this is a rational function that's even over even, we know it's got even symmetry, and so we could have even gone back to our table and done one other thing. We could have even said, okay, well, we know that this thing is also going to be symmetric about the center. So we could make like a fulcrum there, and we could actually, we want to say even. And then we know that this thing is going to be even about that fulcrum, right? It's going to be split. So all we'd have to do when we're making our table, if we wanted to, is we could just make, for example, the right half and be done, and cut our work in half, and then just say, okay, well, the left is going to be a reflection of that, right? So that can be useful too, okay? All right. It's kind of, how different is it to, like, how many, we're probably averaging about one problem a day now in calculus. There'll get a point where we may not even get a full one in one period.